We will now begin the first session of 2016 International Modeling Conference. The first session consists of presentations on marginal abatement cost curves and techno-economic carbon price models for ETS, carbon pricing models, overview of different modeling techniques, and comparison of designing options for ETS and their potential linking in China and South Korea, the alternative discounting value. After the presentation, there will be a roundtable discussion with 3 presenters and another 2 panelists. First of all, we would like to invite Ms. Vicky Dusha from Fraunhofer ISI to give us a presentation titled Marginal Abatement Cost Curves and Techno-Economic Carbon Price Models for ETS. Please welcome Ms. Vicky Dusha with a big round of applause.
Hello. Well, first, let me thank you for inviting me to this conference and for providing me the opportunity to show you what we are doing at Fraunhofer ISI. Yes, as my presentation says, I'm going to be talking about marginal abatement cost curves, the design of marginal abatement cost curves, and then also about techno-economic carbon price modeling, which we at Fraunhofer ISI use for questions relating to the ETS. I will begin with the... slide. I will begin with a short introduction on why we actually need modeling in the context of the ETS. I will then turn to the marginal abatement cost curves, give you some examples, tell you a bit about the characteristics as well as the shortcomings. I will then turn to the techno-economic models, and then I will show you something from a project that we are currently working on for the German Environmental Agency. Okay, thank you. So yeah, let's begin with why do we actually want to model in the context of the ETS? There are 2 points that I want to make in my introduction. The first is that you have to be aware of who's the audience of the modeling. So there are many different participants in the ETS and they have different interests, and it's important to be clear on what those persons actually want from the models, because they may have very different questions. So we have, for example, policymakers who are interested in the design of the policy instrument, but at one point in time also on the evaluation of the instrument. We then have the firms under the ETS who want to know what is the best trading strategy, but also what might be the best mitigation strategy. We have industry associations. In Europe, they are particularly strong and they try to lobby for good allocation rules, for example. So they again have a bit of a different focus compared to the firms that are regulated under the ETS. And then we have financial institutions who are interested in the carbon prices, of course. And then we have a broad set of different questions that are of interest to those different persons. For example, we are interested in the abatement potentials in different sectors, sectors covered under the ETS, but also sectors not covered under the ETS. For the effort sharing, for example, we're interested in the abatement costs related to that abatement potentials. We are interested in cost-efficient solutions because we, from an economic perspective, usually tend to use emissions trading systems because they should be cost-efficient compared to other policies. We want to know what happens if I change my ETS. We might want to know what the interactions are between the ETS and other policy instruments. And for example, in Germany, we have this Energiewende, where we want to reduce our GHG emissions, but also we have other targets with regards to renewable energies, for example, and also energy efficiency. So we want to know how to set our targets to make them fit together properly. Then there are more ETS-specific questions, like different allocation methodologies and what do they do to the firms that are regulated under the ETS. In Europe, we had the discussions on the stability mechanisms under the ETS, and I know, I just learned yesterday that in Korea you have something very similar, so stability mechanisms play an important role. We might be interested in linking different ETS systems, especially now that more and more countries in the world are beginning to implement their own ETS systems. We're very much interested in competitiveness issues. in whether carbon leakage exists and what we can do to avoid carbon leakage. And of course, we are interested in the cost burden that occurs from the ETS to the firms regulated under the ETS. And then, and that is a point where we are right now in Europe, we actually want to evaluate our system after a while, because knowing how it works and whether it actually does what it is supposed to do is an important point, and also in that context, modeling can play an important role. If you think, for example, on projecting baseline emissions, which might have been there if we had not introduced an emissions trading system. Now then we have quite different modeling approaches that can be used, and those different modeling approaches are useful for different questions, of course. The two best well-known approaches, I would say, are the top-down and the bottom-up approaches, which include, among others, general equilibrium models on the top-down side and optimization or simulation models on the bottom-up side. And I'm going to be talking about bottom-up models a bit later, because we have two of those at Fraunhofer ISI. There are attempts to build hybrid models that try to combine the characteristics from the two modeling types. We have integrated assessment models, which are more used in a more global context with regards to how the climate reacts to our CO2 emissions. There are short-term CO2 price models that can be used to predict CO2 prices for the really short run, like tomorrow or next week, things like that. And then we have modeling tools, which can be very handy because they can be designed to answer a very specific question. So from my experience, those modeling tools are maybe the best tool to really do policy advisement, because we can design them to do exactly what we want them to answer the question that we actually want them to answer. And I'm going to be talking about marginal abatement cost curves now, which are one of those modeling tools. So just to sum up my introduction, there are different actors, there are different questions, and we have different models, and it's very important that you make sure that if you have a question, you know who's the actor, what does he want to know, and what's the model that I can use to answer that question. Now let's turn to marginal abatement cost curves, and I'm going to show you a picture that probably most of you have seen before. It's a marginal abatement cost curve. It's a global one, and it was designed by McKinsey a few years ago. And on the x-axis you find the abatement potential in gigatons in this case, and on the y-axis you find the abatement costs in euros per ton. And then you can see what different technologies exist and what their potential is to reduce emissions. And up and around what the costs are that are related to those technologies. This is a very nice illustration because it gives you good to handle information, I would say, on how the world looks. And for us, it is always better if the world is easy and we can somehow paint it in one picture. It makes life easier for us. Maybe brief history. MEC curves, or the development of MEC curves MEC curves were not originally developed for emissions, but they were developed in the context of energy efficiency. In the 1980s already, in the 1990s, they were then extended to cover greenhouse gases. And in the 2000s, they became very popular because McKinsey developed this curve. Also in that context, critics about MEC curves emerged, and I want to talk about that a bit later. So the basic idea is, as I've already said, we have accumulated GHG abatement on the one axis, and we have abatement costs on the other axis. And then we have this curve, and if we have CO2 price, we know that all the potential on the one side of the curve should be cost effective, so it should be realized at one point in time if we face that CO2 price, while the remaining potential on the other side is not realized because it's too costly. Yeah, what's the basis for those marginal abatement cost curves of the McKinsey type? I called them like that, but we could also call them technology-based. Basically, we have a collection of many different abatement technologies. And then we try to order them in an illustrative way to show us the potential and the related costs. If you now want to build your own marginal abatement cost curve, what you basically do is you try to calculate the differences in costs compared to a situation without the technologies, and a difference in emissions, and by dividing the two, you get the specific abatement costs or the marginal abatement costs. This at first sight seems rather easy. It isn't, though, if you try to look into more detail which costs should actually cover it and what you should actually include in your calculations. You can see here that costs are, for example, or can include investment costs, of course, but they can also include running costs, and they will also include energy costs if you look at energy savings. So basically, it seems simple, but if you actually want to calculate the single individual numbers, it's not that easy anymore. 2 points maybe that you should keep in mind. One is the cost perspective that is contained in the marginal abatement cost curves. It is either social or private costs. Social costs means that I use rather low interest rates because I'm more interested in what is the optimum for my society. And from a societal point, interest rates are rather low compared to a private perspective where you would expect rather high interest rates. It has a lot to do with decisions on what the depreciation period for your technologies is, meaning do you take lifetime or do you have much shorter time frames which you look at, like 3, 4, 5 years, what's usually used by firms. Then one other question is whether taxes and subsidies are included in the costs or not included. And again, it depends on whether you look from a private perspective, when you would include taxes and subsidies, or if you look from a societal perspective, where taxes and subsidies are merely a transfer and not actual costs. And then, of course, you have system boundaries from your marginal abatement cost curves. They contain the time frame, the geography, the technologies that you include, whether you include more innovative technologies that might not yet be at the point of being actually available for use, but that might be more in pilot phase or stage. And of course, which sectors are covered by your marginal abatement cost curve. One other point that is important and that we tend to forget every now and then if we look at a marginal abatement cost curve that is presented in this form is the fact that behind all that there's also a baseline that we have to define. So before being able to construct the abatement potential or to calculate the abatement potential, we have to know what are our actual emissions. And that's the baseline. So that is something that can better be seen if you use a different option for presenting the marginal abatement cost curves. The point on the baseline or the reference is that it heavily determines the abatement potential that is contained or that is shown by your curve. Why is that? Because, for example, if I construct the baseline to include, for example, changes in energy prices, then I will see in the baseline already changes in my emissions, and those changes in emissions will no longer be visible in the final curve once I design it by calculating the difference between the reference and the actual mitigation scenario. So it's really, really important to keep in mind that there are assumptions on the reference behind the curves, but that are not really visible. The abatement cost curves are determined by three types of factors that determine our marginal abatement cost curves: input variables and data, methodological decisions, and methodological shortcomings. And most of what I'm saying now I've already said, but it's just a brief repetition. So we have the choice of input variables. As I've already said, what kind of discount rate do I use? What are the energy prices that I assume for my reference, but also for my saving scenarios? What are the technology data that I apply to my curves? What is the technological lifetime? What are activity variables, of course? So production, for example, is an important variable when trying to determine my mitigation potential. And of course, the CO2 intensity of the power supply. And this is a brief example of how the CO2 intensity of the power supply changes the energy efficiency abatement, or the CO2 abatement. You can see here that Poland, for example, who has a rather high CO2 content of its power supply because they're using a lot of coal. Of course, if they introduce energy efficiency measures, the potential to reduce CO2 emissions is much higher at lower cost compared to those countries that have a rather low CO2 content of their power mix, like Sweden or France, who are using lots of hydropower and nuclear. This is an example of how different energy prices or discount rates can change your abatement costs. So constructing those curves was done using exactly the same data except for energy prices and discount rates. Then on methodological decisions, I've already said that we need to decide on whether we want to include or exclude taxes. We have to define our baseline. We have to decide whether we want to look at full costs or if we want to look at additional costs, meaning a cost difference between an alternative technology and the new technology. That makes a lot of difference in some cases. In particular, if you have an electricity market where installations are rather old and you know that you have to build new ones eventually, so it's rather a matter of am I using the one or the other technology than of actually only using new ones. Then you have to, at one point, group your saving options, and you have to decide and have to be clever on how to do that. And of course, you can also decide to include external costs, but that is something that's usually not done in most marginal abatement cost curves. Now let's have a look at the shortcomings. One thing is that it is rather difficult to include scale and learning effects in those kind of curves because our costs kind of are fixed at one point in time. So we normally do not assume that costs go down over time. We have a certain path dependency if we look at the definition of scenarios, and that is something that is often not contained in those curves that only try to or that put focus on those technologies rather than using scenarios. We can have rebound effects. It's a particular problem with energy efficiency, that if your electricity prices go down, you might use more lighting in the house because it's just cheaper for you. You can, of course, have co-benefits, and they are not included. You might forget certain technologies that might be very important. And I think the most important point is the systems perspective aspect, meaning that different saving options actually sometimes interact with each other, and I'm giving you a brief example on that. This is a pumping system which is used in many different industry sectors, and you can have different options to reduce the use of energy in this system. And one provides you 15% savings, another 10%, another 5%. So if you add all of that up, you end up with 45% energy savings. However, the truth is that if you actually do use all those efficiency measures, the total reductions are only 38%. And if you look at, again, if you look at that McKinsey type curve, you would get the impression that your emission reductions might be 45%, but in reality they are only 38%. That was too fast. So a way to better handle this system perspective problem is to use techno-economic modeling. And that is what we do at Fraunhofer ISI. We basically have a very good database on mitigation technologies, and we build a framework, a modeling framework around that, that database that allows us to use those data in a very systematic way to create scenarios, to vary certain parameters very systematically, and to being able to analyze the results. However, you have to keep in mind that in contrast to that very simple illustrative way of marginal abatement cost curves, handling such a model is rather complex. It takes time to build the model, it also takes time to analyze the modeling results, and it also needs some expertise. So it's not something that you can just hand over and say, okay, now you do your own analysis and everything is fine. So let me show you a bit about the forecast model. The forecast model is a model for, it was originally designed for the modeling of the energy demand, but we have now also included the modeling of GHG emissions. It contains, well, it is technology-based, as I've already said. We predict the final energy demand. It includes all demand sectors, basically. It includes the EU 28, as well as Norway, Switzerland, and Turkey. It's a simulation model, and it is long-term, so we do predictions or projections up to the year 2050. And as I've said, we are also able to project GHG emissions. It contains different parts, the industry part, a tertiary part, a residential part, and an others part, which includes agriculture and transport, but that is rather to get an overall picture than anything else. And I'm going to focus on the industry part in the next few slides. I think I'm going to skip that. So basically, this is a very simplified structure of the industry model. I hope that doesn't mean anything. So we have information or assumptions on the production in each individual sector. We then calculate the energy demand based on specific energy demand figures that we have. We can then calculate saving potentials on a process basis, meaning saving potentials that are actually related to the production process itself. And then in a second step, once we have the remaining energy consumption, we can also calculate the saving potentials related to cross-cutting, so-called cross-cutting technologies. Cross-cutting technologies are technologies that are used not only in one precise industry, but basically in overall industry sectors. To highlight that, basically, you know, if you produce steel, for example, you have those things that are really related to steel production, like the furnaces or the electrolysis. But then on the other hand, we have things like lightning or pumps or motors that are used in all industry sectors, and we model those as cross-cutting technologies. Forecast has a hierarchically structure, which starts with the industry. We then subdivide the industry into subsectors, like iron and steel, chemicals, paper, and so on. It corresponds very much to the sectors that are differentiated in the EU ETS. We then have processes. For example, for paper, we have the production of the pulp and then the production of the paper itself. That is the process part. We have the cross-cutting technologies part, where we look at things like pumps, motors, lightning. And then we have the saving options in those two, on those two sides. We have a similar model for the electricity market, which is called Anatile. And how much more minutes do I have, actually? Any ideas? Who's trying to keep track of the time? 2 more minutes? Or 2, okay. So I will skip the Anatile part. It's basically a model of the electricity market in Europe, and it's an optimization model. We also have a simulation part, but it basically works very similar to forecast. So one last thing that I wanted to show you is that we are currently using the two models to develop marginal abatement cost curves from those techno-economic models, because in that way we are able to combine the good characteristics from both sides. So marginal abatement cost curves allow us an easy handling and are very illustrative, while on the other hand, the techno-economic models allow us to use or to include the system perspective that is not included in the originally technical marginal abatement cost curve. And we do that by running our models several times with different CO2 prices, and by calculating the difference between our baseline scenario, which has a CO2 price of 0, and our CO2 price scenarios. However, what we find right now is that it is really important to make sure in the beginning what you put into your baseline and how to define your CO2 price scenarios in your baseline scenarios. And we actually are spending quite some time on finding a good definition of our reference scenario at the moment, defining the interest rates that we should be using, defining the technologies that we could include or should include or not include, and in particular defining the policies that should already be included in the baseline. Like, for example, renewable energy policies, which are particularly interesting or relevant for the electricity sector in Europe. We've already done that exercise for Germany for the industry part and came up with such a marginal abatement cost curve. However, our ministry did not really like it because the abatement potential is rather low in industry, and that is the major factor which made us think about the reference so much now. This has a lot to do with the fact that we already see abatement in the reference scenario. So right here we only see 7 more tons abatement at a price of 50 euros. However, already in our baseline, emissions are reduced by around 20 million tons. So it's just a big, huge difference. Yeah, pretty much said that. We decided for this exercise to link our models in that way that we are using electricity prices from Enertile for the forecast model, but we decided not to include the energy demand from the forecast model in the Enertile model. That is related to the reason that industry is only one sector on the demand side for energy, and other sectors like buildings, for example, are not covered under the ETS, but they make up a heavy part, and we think that the impact on electricity prices should be rather low. Yeah, to wrap up, quantitative modeling is very helpful in designing and evaluating emissions trading system, but also in answering other questions relating to climate policy and energy policy. But different questions come from different actors, and you need to decide what the relevant model is to answer your questions. McKinsey-type marginal abatement cost curves can be very useful because they are simple to understand. However, they do not cover systematic or system aspects, and that is quite a bit of a problem. You also tend to forget that there are underlying assumptions that cannot be seen from that picture, like the reference, like energy prices. Techno-economic modeling is a way around that, and I've just shown you that we are currently trying to develop meaningful marginal abatement cost curves from our techno-economic models. However, a lot of attention needs to be given to the definition of the scenarios when doing that. And with that, I want to thank you for your attention.
Thank you, Ms. Vicky Dusha, for your wonderful presentation. Next, Dr. Jan Lichtstein from Fraunhofer ISI will give us a presentation on carbon pricing models, overview of different modeling techniques. Please welcome Dr. Jan Lichtstein with a big round of applause.
Yes, my name is Jan Lichtstein. thank you a lot for the invitation. It's a great honor to speak here. I'm from the German Institute for Economic Research, the DIW Berlin. And I'm going to give a more general introduction to different models that are being used in policy analysis and economic analysis of carbon markets, and also going to give a few examples of that. I'm also going to give potential market failures that might need to be considered when modeling carbon markets, as well as presenting a multi-model analysis that was done by colleagues of mine at DIW, but also by fellow speakers Luca Tascini and Harrison Fell. So the first question, or the first point to consider when starting modeling is that you actually should consider the goal you have in mind when modeling carbon prices. And there might be different reasons to do so. You might simply want to do an ex-post analysis of price developments in existing carbon markets. You might want to do short-term price forecasts. You might to develop long-term price scenarios, and in there you would not only be interested maybe in the prices that develop, but also the long-term transitional aspects which technologies are applied. And I want to point out that I'm speaking about price scenarios, not price forecasts in the long term, which are not really possible, I would say. You might want to investigate different price drivers and price dynamics. These could be technological aspects, but also economic and social. You might want to evaluate different carbon pricing policies. This is the direction that I was coming from, to have a look at different design options for the EU ETS to potentially stabilize it or make it more efficient, to achieve more efficient abatement options. And not to forget, a lot of times models can also be used to communicate ideas, to explain different policies and their effects. And I think that is a point that should not be underestimated. I'm going to compare different model types across different dimensions. The first dimension definitely is the time scale. You could have a look at more short-term aspects of carbon markets, let's say within a year. You could even go further down to, let's say, intraday trading, but let's say for policy analysis, I think aspects of around a year may be relevant. Then you have medium-term models and of course also long-term transitional models that go up to 50 years in time. Another important question you should ask yourself is which scope of the model are you interested in? Is it entire economy effects that interest you the most? For example, would you like to know what is it going to cost to reduce emissions? Is it maybe 0.5% of your GDP or 2%? Maybe you are only interested in actually looking at the sectors you're analyzing. In that case, you would look at the entire ETS. And sometimes you're also looking at subsectors, for example, the electricity sector or also the industrial sector. There's also the geographical aspect. Are you only looking at an individual country, or maybe worldwide effects? Is carbon leakage of concern, or trade with other regions? As Vicky Dusha has pointed out, one important aspect is the technological detail. Are you basically using aggregate functions, technological functions, to estimate costs in sort of an aggregate way, or are you actually modeling each individual technology from the bottom up? One final aspect is aggregation and heterogeneity of actors that you're representing in your model. Are you using, let's say, big representative actors? Let's say one actor for your labor demand, one actor for your industrial demand, or actually, are you actually going down into more different actor types or even individual actors that are making decisions in your model? Coming to the potential market failures, the first three market failures sort of have a common effect in the model. The last one is slightly different. So what we have seen in Europe is that we have limited banking capabilities, or limited banking is taking place. If you use, let's say, very perfect foresight models, you would actually estimate actors to start saving and banking a lot of emission certificates now, up to 7, 8, 10 years of accumulated emissions, because the assumption goes as time progresses, we are going to make technological progress, and it's going to be cheaper to reduce emissions in the future. And one of the reasons that this might not take place is that we actually have different type of actors which have different capabilities of banking their emission allowances. So what you see here is are some results from a model of ours. In the top graph, you see the banked emissions or the banked emission allowances in the EU ETS in a simulation with two different actor types. One are hedgers and the others are speculators. So hedgers are basically, in this model, electricity companies that sell electricity into the future. So in Europe, very often for 2 to 3 years ahead of time, electricity companies will sell future contracts. And when they sell these future contracts, they also buy all the ingredients basically to make that electricity. So that could be coal, that could be gas. But of course, since we have an EU ETS, they also need emission allowances as an ingredient. So what they will do is they will also buy these emission allowances ahead of time because they've also sold the electricity futures ahead of time. And since this is basically a risk mitigating measure, the interest rate applied for this sort of hedging behavior is rather low. It will be basically a risk-free interest rate of maybe 3, 4, 5%, which is very close to the social discount rate that a social planner would use. On the other hand, we have speculators in the market that actually see that in future probably carbon prices are going to rise. However, in order to speculate, they want to get a return on their money. They wouldn't invest it, they only get a 2% interest rate of return. What they would actually want to see is 10, 15% rate of return on their investments. So they will only enter the market when they will forecast carbon prices to actually rise very rapidly in the future. So what is the effect on an expected CO2 price development in different models? In the gray line, you will see a CO2 price with banking at 3%, which is very often assumed to be sort of a social discount rate, what a social planner would like to see. And you see that the CO2 price starts at a medium level and then rises very slowly into the future. If you have this difference between hedgers and speculators, what you will actually see is that in the beginning, you will have rather depressed prices, and only later they will sort of rapidly rise because in the initial years, important investments to reduce emissions have not taken place. The other potential market failures, such as regulatory credibility, will have a similar outcome, but maybe a different underlying reason. Companies face regulatory uncertainty. For example, the parameters of an EU ETS are possibly changing in future. You might see a different cap setting. You might see a linking of the ETS to other countries. As in case of Australia, an ETS might totally be overturned. And then the question is, do companies want to actually bank emissions for the next 20 or 30 years, or are they only willing to look ahead, let's say, 5 years over time? And that is actually very important from a policymaker point of view to actually have a reliable framework that is credible. Another point which also has sort of a myopic effect is bounded rationality, the uncertainty and complexity. Companies might not be able or not be willing to actually forecast 20 or 30 years into the futures. They might have incomplete information about other companies, and their decision processes might actually not be designed to take all this uncertainty into account and rely on simplified representations of complex situation and instruments. One example, if you look at the World Energy Outlook, usually the oil price is forecast in sort of a linear fashion based on the current level. This is what we very often assume, and it's also maybe our best of knowledge. But as you all know, the oil market is basically not really able to forecast it. So this is something that also makes companies to behave in a more myopic fashion. They will rather concentrate on the next 5 years than rely on some forecasts for 30 years ahead of time. And finally, we might have market power. only relatively few companies may produce a large share of emissions in an ETS. This may create the potential for exercise of market power, and of course, it depends in what situations these influential companies are. Do they have, let's say, an over-allocation, meaning that they actually want to sell all their or a part of their certificates? This would make it an oligopoly. Or are they maybe under-allocated that they actually need to buy emission allowances? In this way, they could also exercise market power, but actually from a buyer's point of view, an oligopoly. Coming to the different modeling types, I've got here roughly 4 categories. One is more econometric, then some numerical models, equation-based model, let's put it like that, simulations, which sort of do a stepwise simulation of results, and analytical models, where you basically just take a pen and paper. So econometric models are basically just a statistical analysis, although sometimes very elaborate analysis of historic economic data related to carbon prices. Usually these are more used for short to medium term analysis. Of course, you can also apply statistical analysis over the last decades. However, you need to have a very good data set. So you would need to have some years of past data to actually start with a more interesting type of analysis. The scope is very flexible. It depends on the data. And we're actually not modeling in rich technical detail. This is not really applicable. A very relevant modeling class are general equilibrium models, most notably computational general equilibrium models. In Europe, this would be JME3 model or the PACE model. These models are very large-scale models that rely on basically imposing equilibrium conditions on the entire economy, underlying it a social accounting matrix. And usually these will make assumptions that are equal to perfectly functioning markets. They have a very high scope. They will cover the entire economy, maybe even multiple economies on a worldwide scale if you use the GTAP database. On the other hand, their technological detail is rather low. Sometimes some of these models will include modules to actually model some sectors in more technological detail, such as the electricity sector. If we are looking at models that cover the energy system, and the actor aggregation will be very, very high. We only have one representative actor for each big part of the economy, like the labor force or industrial production. If we want to actually analyze more specific policy questions, partial equilibrium models are of use. These are also equation-based models, but we really focus more on a limited part of the economy. They are a lot more tractable, so they can be more easily explained to other stakeholders. Other modelers can more easily read them and actually grasp very quickly what they're all about. They can also be more easily made to incorporate market failures, include a bit more technological detail, disaggregate some of the actors into subgroups. For example, the model that I presented earlier on the actor disaggregation into speculators and hedgers was a partial equilibrium model of the ETS developed at DIW. And per definition, they're very limited in scope. They will focus, for example, only on the ETS sectors or even maybe subsectors like the electricity market. We have cost minimizing models, as Vicky Dusha presented earlier on. These are social technological models. These often rely on optimization approaches, can also be simulation approaches, and usually they're limited to the supply side. They can also cover demand options, but then these are more of a technological detail. It's not really describing the social nature of demand. It's more difficult to incorporate market failures since they sort of assume optimal behavior on part of the technologies, and they can operate all the way from the very short term, maybe operation of the power system, to the very long term. We have simulations, which is my domain. These are sometimes agent-based models, sometimes other models. There you actually describe behavior or technological details from the bottom up. Here in agent-based models, actually actors are modeled as boundedly rational. All these actors only have some information at their disposal. They will try to make fuel price forecasts electricity price forecasts, demand forecasts, and based on their limited information, they make decisions in the model, and they might be wrong about their decisions. So what will happen is that you might see market cycles, peak cycles, investment cycles, and this is very interesting to analyze the stability or the robustness of policies due to imperfect behavior of agents. One of their problems is that they have only a limited tractability. These models tend to be rather large. The model that I developed had several thousand lines of code. It's open source, but on the other hand, who has the time to read through all that? So they are a bit of a black box approach. On the other hand, in comparison to other approaches, they are relatively cheap to run. That lends itself to sensitivity analysis, to Monte Carlo analysis, to really analyze the system under various circumstances and developments. Finally, we have analytical models, which could be partial equilibrium models, for example. These are very limited in scope, and these are basically equation-based models that you solve with a pen and paper. They're extremely tractable. They are more of an academic context, but they're very good to develop ideas, to generate theory, and explain policy implications in a more general fashion. Coming to the multi-model analysis, this was a study of the Market Stability Reserve in Europe, which is a quantity-based instrument. It basically looks at the EUAs, the EU emission allowances in circulation, and when they're above a certain threshold, 833 million of EUAs, 12% of these emission allowances are basically put into a reserve. Then you have a target corridor of emissions allowances in circulation where nothing is happening, and then below another threshold, these EUAs are again injected into the EU ETS. And what was done in this model comparison study is that several research institutes and people came together to basically harmonize their models. They not harmonize the models, actually harmonize the evaluation framework and the input data. So all the same input data was used. The marginal abatement cost curve was derived from a general equilibrium model and was input into these different models. Different key criteria were developed to analyze the effectiveness, the efficiency, the robustness of policies, and these were basically then compared for different model and types. Let's say indicator for the intertemporal flexibility from 0, assuming no banking, to all the way to a perfect banking behavior by all actors. And the good thing was that all these models had different market failures that they took into account. The DRW model that you saw earlier in the graph showed limited capacity of banking behavior. Then we had myopic behavior in the model from the LSE and from Raphael Trantillon from CEC. And we had models that took the complexity information limitation of actors into account. And how such a model comparison can look like is that if you have a look at the efficiency criterion, sometimes models disagree in the evaluation of different results. So for example, for the no MSR case, some models in this comparison study basically said the EU ETS would perform terribly badly, whereas other models says, well, it would be sort of doing okay. Whereas if you introduce a market stability reserve in either the original design or in an early start case, these models would show an improvement. And the interesting point is that while these models were widely disagreeing for the effectiveness of the EU ETS in its pure form, in introducing a market stability reserve, they sort of shared an aggregate view that this is actually not a bad idea. And I think that's a very powerful tool to use different models with harmonized data and harmonized frameworks to look at them and see do we get robust results for certain policies, or is there maybe some difference in outcome according to our assumptions. So I'm already coming to my conclusions. So first of all, different modeling goals lead to different models. There's no one size fits it all. For economy-wide effects, I think currently general equilibrium models cannot be really substituted. I know that some agent-based models are in development for large-scale systems, but I think they have not really reached full fruition. I would also really recommend looking at sector-specific models, specifically small, easier to understand models. These can lead to deeper insights into the markets. They are more easily done to communicate them to policy stakeholders. They're easier to understand. Modelers can maybe also learn a bit more from them. And I would also like to point out that several potential market failures can exist in carbon markets. Before really starting to model, it's important to analyze the market to determine which market failures might apply, possibly also market failures apply that I have not listed here. And finally, for policy analysis, I would always recommend using a multitude of models of different modeling types to actually look at the problem and arrive at robust policy solutions. Thank you a lot for your attention, and I'm looking forward to the other presentations.
Thank you, Mr. Jo Lichtenstein, for your wonderful presentation. Finally, Mr. Morgan Krenes from Enerdita will give us a presentation on comparison of design options for ETS and their potential linking in China and South Korea, the alternative discounting value. Please welcome Morgan Krenes with a big round of applause.
Thank you very much. Good afternoon. Thanks very much for inviting me and Enerdata to the IMC. It's a real pleasure to be with you today. So the topic is still about carbon pricing modeling. And in this presentation, we'll be looking more closely to different options for ETS design. So we look at China, South Korea, and 4 design options, and with a specific focus on the concept of discounting value. In the first part, I will briefly present Enerdata, my company, and our forecasting tool and activities. I will present the tool we use for this study. And in the other parts, I will present the study itself, beginning with the key assumptions, key results, and limitations and potential for further work. So Enerdata, this is an independent energy research and consulting company founded in the early 90s as a spin-off from a research center specialized in economics and energy. Our head office is located in Grenoble, in the French Alps, and we have also a growing office in Singapore. Our activity is global. We have projects and clients all around the world. So our core activities address several issues, strategic and business planning, as well as policy making. We do it with different time horizons, from historical trends to forecast analysis. It can be global, local, and it is supported by a range of different tools and models with top-down approach, bottom-up approach. Our field of expertise, we have 3 main fields of expertise: market study, energy efficiency and demand, and global energy forecasting. So I'm working in this team, and we use extensively pulse model to produce analysis and forecasting results. So on our website, you will find several interesting and recent papers or projects: Global Energy Trends, EnerFuture, which is the equivalent of the World Energy Outlook from IEA, and COPEC, a private public research project focusing on the EU ETS revision. As I said, we are running various models and tools. For this study, we use specifically Pulse model and Evaluate. So Pulse is a world simulation model, hybrid. There is a bottom-up approach for power sector, but also a top-down approach for final demand sector. It's a global coverage, 60 countries, regions, covering all the world, with a long-term time horizon, up to 2050. From Pulse, we'll extract marginal abatement cost curve, and it will be used as input in the Evaluate tool. This tool is a very user-friendly tool that allows you to design different climate policies. And then you end up with very interesting indicators, market prices, reduction per sector, per country, etc. So POLS. POLS stands for Prospective Outlook on Long-Term Energy Systems. The objective is to analyze and forecast supply, demand, and prices for energy commodities. So it's very useful for assessing the impact of climate or energy policies. This model was developed in the 90s and is currently used and developed by 3 entities: Enerdata, Eden, a French research center, and JRC IPTS, a research center of the European Commission based in Sevilla, Spain. Sorry. So the strength of POLS is putting together supply, the production of oil, gas, etc., and demand, as well as prices. So it will model the interactions between them, but also between markets, energy markets, and between countries. So the main inputs of this model are macroeconomic assumptions, such as GDP or populations, which are exogenous to this model. And the main output will be consumption per country, per sector, per fuel, production, emissions, and prices, market prices, but also end-user prices. Coverage is global, 66 countries and regions, the full J20 countries, including South Korea. And a very interesting feature of POLS model is its ability to produce MAC curves, marginal abatement cost curves. What are MACs with POLS? Very simply, it's a sensitivity on carbon value. So the carbon value will impact energy prices based on the carbon content of each fuel. And in return, you will have an impact on demand and emissions. So we can produce MACs for all countries and regions, for 20 emitting sectors, different GHGs, and for all year from 2020 to 2050. So this raw material is very valuable for further analysis, especially climate policy analysis. Now I will show you how we build MACs with POLS. So everything starts with defining a baseline scenario. This is very important. So from this baseline scenario, you will end up with baseline emissions for a given sector, a given country, and a given year. And then you will proceed to the carbon value sensitivity. So for each increment in carbon value, you will have additional emission reduction. And at the end, you will end up with a full marginal abatement cost curve. So how much it will cost to reduce an additional unit of emissions. So marginal abatement cost curve are very useful. Given a reduction target, you will have the marginal cost, the market price, or the value of a tax you would have needed to achieve a certain level of emission reduction. And with the area below the curve, you will be able to calculate a total abatement cost. So here you have an actual example of MACs from POLS for China and South Korea. So the horizontal axis is not the same scale, of course. And you can see that the potential per sector is not the same. The relative position between sectors is not the same for both countries, but power sectors in blue is the main source of reductions in both countries. So all these MACs are then implemented into the evaluate tool. So you can design your ETS market or other policies such as carbon taxation or regulation. And the output will be reduction emissions per sector, per country, level of trading, marginal cost, and other interesting indicators such as emission intensity. Okay, so I have presented you our tools, and now I will present the study itself, starting with the key assumptions. So what's the objective? The objective is to look at 4 different ETS design. Domestic ETS, without a link between the jurisdictions, so we're looking at China and South Korea. Full linking between China and South Korea. So we'll see that with this direct linking, we'll be able to reduce strongly the cost, but because of a strong import level from China to South Korea, so it means that there will be a very big financial transfer between both countries, and at the same time, domestic reduction in South Korea will be relatively low compared to the domestic ETS only scenario. So in the 2 other scenarios, we look at how we can handle this, limit financial transfer, and having significant domestic reduction in South Korea. So we look at the discounting value concept and a very simple trading cap for imports-exports between China and South Korea. So this study was initially developed as part of the Network Carbon Market Initiative. So this project is led by the World Bank. And the purpose of this project is to link mitigation actions between jurisdictions and countries. So what's the framework? As I said, we're looking at China and South Korea. The target here is 2030, so it's rather a static analysis. We are looking just at 2030. We have a strong assumption for ETS design. All sectors are included in ETS, in both China and South Korea. And then a very important question, what will be the reference scenario for this study? So before we start doing the sensitivity on carbon value. We made the decision to replicate a baseline scenario from World Energy Outlook, WEO 2013 current policy scenario. Because if we start using business as usual given by the country's own forecast, we'll not have enough information. It will be very difficult to model it. We might have some information for 2030, but it's not enough, and it's more efficient and convenient to use a full baseline scenario we can easily replicate in our model. So we have our baseline. Now we have to define what are the objectives. And for both China and South Korea, it will be based on the INDCs. We can see that the definition of the objective are not the same in both countries. It's not the same type of target, not the same base year. For China, we have a range of mitigation effort, a single value for South Korea, 37% effort. But for both countries, this is a market-based mechanism, an ETS. So the next step is to quantify all these objectives in our model. So here you have the results. And for China, you can see that we use the 65% target. So we are not saying that the 60% target is not ambitious enough. It's just that for analysis and modeling reasons, it's more interesting to have a more significant reduction in China. So now we have our baseline scenario, we have our cap. And in this slide, you can see what's the baseline level for both China and Korea, where is the cap, and historical trends. So if you look at the cap in China, you might say that it's relatively higher compared to South Korea, compared to the baseline. But you have to take into account the historical trends and also, of course, other political and economical factors. Some additional assumption we made for this study. So the market price is linearly evolving from 2015 to 2030. And something important, the target between sectors and the allocations are distributed based on the baseline emission weighting. Again, all sectors represented in polls are implemented in ETS for both China and South Korea. Now the key results. So we have 4 scenarios. As I said, direct linking will have strong reduction in abatement cost with very large level of imports, but it will imply large financial transfers and very low domestic reduction in South Korea. So we are looking then in a scenario with discounting value and cap on trade volume to limit financial transfer and to have significant domestic reduction in South Korea. To begin with, so you have the emissions in the first graph for China in blue and South Korea in orange, then the marginal abatement cost and the abatement cost. You can see that, the marginal abatement cost at the bottom. So if you are just looking, for example, to South Korea in orange, you can see that, for instance, you have not the same level of marginal abatement cost because it depends on the target for each sector, but also the energy structure. For instance, in road transportation, energy demand will be quite inelastic to energy price. So now we are looking to domestic ETS only, no link. And for South Korea, what you can see is that you will end up with a single market price, $310 per ton of CO2. And now all the sectors where it's quite expensive to reduce emissions, they are able to buy permits on the market. So what happens? If you look at this graph, you can see that suddenly South Korea can divide its abatement cost by 3, just by putting in place a domestic ETS. So it's very profitable also for China. And if we look at the trade, the level of trade for China, so these two graphs represent what we have in China, we can see that some sectors like power sector are net seller of permits on the domestic market. So now the key conclusion for this scenario. So we are achieving the same reduction than in the without domestic ETS, but the costs are strongly reduced. And some sectors are net seller, power and manufacturing. Other sectors, such as transport, chemical and mineral productions, are buying on the market. So now we link both markets, Chinese and South Korean ETS, and we see what happens. If you look at this graph, in orange, you will have the level of trade for South Korea. So in orange, it's the direct linking scenario. What you can see is that all sectors becomes net buyer on the market. So it means that South Korea will start buying permits to China. And the abatement cost on this graph, you can see that domestic abatement costs in orange with a direct linking scenario are very low. It means that suddenly South Korea will stop reducing domestically its emission, and it will prefer to buy permits on the market from China. So with direct linking scenario, the same emission reduction is achieved compared to domestic ETS. And global costs, so abatement cost in China plus abatement cost in South Korea, are strongly reduced. But the issue, as you can see, is that it implies a large financial transfer. And at the same time, emissions reduced domestically in South Korea are very low, which is not a very good signal. So now we'll see what we can do to handle this, to have optimal reduction costs, but at the same time limiting financial transfer and having a strong reduction emission domestically made in South Korea. That's why I will introduce the concept of discounting value. So in this graph, you have country A in blue and country B. So country A will be South Korea, let's say, and country B will be China. So what's a discounting value? It's very simple. It means that, for instance, with a 50% discounting value, country A, South Korea, must buy 2 permits from country B, China, to reduce its domestic emissions by 1. So this marginal abatement curve, so it's a theoretical one in orange, let's say it's China, perceived from South Korea in blue, it will be less interesting to import from China. So it means that the slope will be higher. And because we have a 50% discount value, it means that the slope will be twice higher than previously. What's very interesting with this concept of discounting value is that there is an optimal discounting value. So in this graph, in blue, you have the total emission reduction, China plus South Korea, or country A plus country B, in blue, and in red, the reduction target, for the sum of the reduction target for both China and South Korea, or country A and country B. So there is an optimal discounting value at around 0.3 that maximize total emission reduction, and at the same time, which is very interesting, for this discounting value, we still have lower total abatement cost compared to domestic-only ETS, so without any link. So you can see that there is a specific shape for the total emission reduction. So there is the first zone. So for very low discounting value, it's not profitable at all for country A to import permits from country B. It's too much discounted. So it's the same as domestic ETS with no link. And then in zone 2, it will become interesting for country A to start importing permits from country B. So we have higher total reductions compared to the target, but lower abatement cost compared to domestic ETS only. And then you have the last zone, zone 3, where if country A imports 1 permit from B, it will be more than 1 on the domestic market, which doesn't make sense. So it's just a theoretical zone. You can forget it, actually. So now, our scenarios with discounting value. We have looked at two sub-scenarios, discount 1 and discount 2. Discount 1 with this optimal value of 0.3, and discount 2 with an intermediary value of 0.5, so between the optimal one and the direct link equivalent discounting value of 1. Because with a direct linking between two markets, it means it's equivalent to say that there is no discounting or that the discounting value is 1. It's the same thing. So as you can see on this graph, total emission reductions are higher than with the direct link scenario. And in South Korea, with the discount, when you move from discount 1 to discount 2, because you're less discounting in discount 2 scenario, it's more interesting for South Korea to import from China. So there will be less domestic reduction scenario, reduction in South Korea when the discounting value is increasing. So here is the analysis. So I just said that with discounting value, when you are increasing your discounting value, you will have more import, less domestic reductions. So it means that with the discounting value, compared to direct link scenario, you will have more total reductions, which means more abatement cost. So you can see it in this graph. So in conclusion, for this scenario, with a discounting value, you can achieve higher environmental integrity. As you can see it, we have more total abatement reductions compared to the target. Because we are using this discounting value, we will have more domestic reduction in South Korea. So it starts being acceptable, politically acceptable to have this level of import or export from China to South Korea. And then the issue is how much we want to do to reduce domestically in South Korea, and how much we want to limit financial transfer between China and South Korea. Because in this scenario with the discounting rate, we are overachieving the total reduction target. We are now looking at an alternative, a pure trading cap scenario. In this alternative, we use a trading cap of 79 megatons of CO2. And this value is not random at all. It's the value we need to have the same domestic reduction in South Korea with this level of trade cap compared to the discount one scenario. So the scenario is this optimal discounting value. So you can see in this graph that in orange, domestic reduction in South Korea is the same. You can see it also on the graph on the left. So with a trading cap, you are sticking to the reduction target. You are not overachieving it. And of course, you are limiting your imports from China compared to the direct link or from the discount one scenario. In terms of discounted emission reduction, so when you apply this 0.3 coefficient, you can see that in the discounting scenario, you have the same, let's say, discounted imports in trading cap scenario or discounted scenario. So with a trading cap, you are limiting exports. And as you are limiting export from China to South Korea, you have less domestic reduction in China, which means less total abatement cost in China compared with the discount one scenario. So yeah, the discount value will allow higher environmental integrity. So we are going above the target. So it means higher abatement cost. With the trading cap, we still have we have the same domestic reduction in South Korea compared to the discounted scenario. So the difference will be in the domestic reduction in China. So you can see that if we are looking at the abatement cost, we have the same reduction cost in South Korea, but in China it will be lower with the trading cap. It's just because we are sticking with the cap, with the target. We are not overachieving the target. Of course, in the direct link scenario, it's much more efficient economically. It's optimal, but as you can see, abatement cost, domestic abatement cost in South Korea are very low, which means that there is no domestic reduction in South Korea. So, in conclusion, when you compare all the scenarios, so by modeling the scenario, you can see that there are different options. You can have a full linking, a discounting value, or trading cap. Discounting value and trading cap allows you to have significant domestic reductions in South Korea compared to the full linking scenario. And then the next question will be, what should we use? What value should we use for the discounting value? And what cap should we use for limiting the import-export between both jurisdictions? So this is not the modeling which will give you the answer. Modeling can give you what will be the figures and the abatement cost or the level of reduction, domestic reduction in both China and South Korea. Then you have to, it will be more a political, social decision to be made, and it will go beyond pure modeling. Another comment, in the trading cap scenario, it's not completely separated from the discounting scenario, since to have a very interesting CAPE value, it requires to have the actual domestic reduction in South Korea we had with the optimal discounted value. So there is a link between the trading cap value you can have, what should be the right one, and the optimal discounting value you had in the discounting scenario. So now I will present you some limitations and potential for further work about this study. It's more about modeling now. So we are looking at 2 jurisdictions. Our tool can handle more jurisdictions, at least 3, and we could develop this tool to have more jurisdictions. We could implement access to international credit because POLS is global. We have max for all countries and all sectors in the world. So we could see where we could find very cheap emission reduction. The design of ETS coverage is quite simple in this study because all sectors represented in POLS are included in ETS. And we could select, if we want, what sector we want to have in the ETS. It's rather a static analysis. So we are looking just at 2030. What we could do is look at other year, let's say 2020, 2025. And this will allow us to find the optimal pathway to achieve the 2030 objectives. Okay, so thank you very much for your attention.
Thank you, Mr. Morgan Cranes, for your wonderful presentations.